Okay, um, good day, students. Um, Today we'll be looking at the part 2 of the NECO 2021 NECO Physics that was written on Thursday 29th of Thursday 29th of July 2021. And as I've said in part 1 that NECO this year was written before WAEC, that in the recent times we used to write WAEC before NECO, okay, here in Nigeria. Okay, so we started in part 1 with objective questions, so I was able to explain and then explain number 1 to 20 in part 1 of this particular subject, physics. Okay, I was able to explain number 1 to 20, and I've given the correct answers through my explanation. So in this part 2, let's continue from 20. The next question will be 21. So when we are done with that, we'll go into the theoretical aspect, the theory aspect of the exams. Okay. The first, don't forget to click on the subscription button. Just click on it, and the like button, okay, to see the video, the part 1 video, okay, and the other videos that I've uploaded on YouTube. Okay, so I remain Campus Academy as usual. Campus Academy as usual. You know what keeps me going is what? My water. Water is life. Water is life. Yeah. Okay, life is simple as usual. Okay. All right. Okay, let's start from number 21. Number 21 says, this is NECO. Okay. Number 21 says a wave of wavelength 1 kilometer. A wave of wavelength 1 kilometer is transmitted through a broadcasting station. Calculate its frequency. I repeat, a wave of wavelength 1 kilometer is transmitted from a broadcasting station. Calculate its frequency. So we have been given C as 3 times 10 raised by 8 meters per second. A wave of wavelength, let's list out the parameters first. The wavelength is represented by lambda equals to 1 kilometers. 1 kilometers is converted to meters by multiplying by 1000. 1 kilometers to meter multiply 1000. That is 1 times 1000, and that gives us 1000 meters. 1000 meters. So that is the wavelength. We use lambda to represent wavelength. Okay. Then we are given C, small letter C, that's speed of light in air, 3 times 10 raised by 8 meters per second. 3 times 10 raised by 8 meters per second, that's the speed of light in air. Okay, and we have to find frequency. Frequency is represented by small letter F. Frequency equals to question mark. So the question says a wave of wavelength 1 kilometer is transmitted from a broadcasting station. Calculate its frequency. And you know a wave is a disturbance which travels through a medium and transfers energy from one point to another without the movement of the medium itself, without the actual movement of the medium itself. So the suitable formula here is V equals to F lambda. V is equal to F lambda, and that V is same thing as C, as speed. That V is same thing as speed as C. Are you there? So C equals to F lambda. Okay, let's substitute our values. Our C is 3 times 10 raised by 8. We are looking for F, frequency, multiplied by the wavelength. Wavelength is 1000. So making F the subject, we have F equals to 3 times 10 raised per 8 over 1000. Okay, and 1000 is 10 raised per 3. So at the end of the day, we have 3 with your calculator. We have 3 times 10 raised per 5 has. Okay, 3 times 10 raised per 5 has. Okay, that is the final answer for number 21. And the option here is option A, 3.0 times 10 raised per minus 8 as. Option B, 2.0 times 10 raised per minus 5 as. Option C, 3.3 times 10 raised per minus 3 as. Option D, 3.0 times 10 raised per 5 as. And option E, 3.5 times 10 raised per 5 as. So you can see that the correct option is option D, 3.0 times 10 raised by 5 as. Okay, that's for number 21. That's for number 21. Okay, so let's go to number 22. 22 says, which of the following waves requires air for transmission? Which of the following waves requires air for transmission? Which of the following waves requires air for transmission? A, infrared. B, light. C, radio. D, sound. E, water. So A, infrared. B, light. C, radio. D, sound. E, water. Okay, so now when you look at types of waves, we have mechanical waves and electromagnetic waves. Okay, you can see that examples of electromagnetic waves can be represented by this acronym, REVOS. These are examples of electromagnetic waves that do not require a material medium for their, or that do not require material media, plural, for their propagation. Radio, infrared, visible, ultraviolet. This is radio wave. This is infrared ray. This is visible light, the light that enables you and I to see. Ultraviolet ray, X-ray, and gamma ray. So these ones are the examples of electromagnetic waves that do not require a material media for their propagation. Are you there? But we also have the second, which is mechanical waves. Mechanical waves require material media for their propagations. Are you there? Examples are water wave, sound waves, and then wave generated from a string fixed at one end or fixed at both ends, and the likes. Okay, so when you look at the options, we have infrared. Which of the following waves required air for transmission? Air for transmission. Infrared ray, that one does not require that. Infrared is wrong. Radio, option C, radio is wrong. Light, option B, light is also wrong. Light represents visible light. So option A, infrared, option B, light, option C, radio, they are under reversed. So those ones are wrong. So look at D, sound wave and water wave. Sound wave and water waves, they are examples of mechanical waves. They require material medium for their propagation. The water wave requires water as the mode of transmission for its propagation. Are you there? Sound wave requires air. So sound wave requires air for its propagation, for its transmission. So our correct answer is D. Which of the following waves requires air for transmission? So it's sound wave. Option D. So number 22, option D is correct. So let's go to number 23. Number 23 is, there's a diagram for number 23. There's a diagram for number 23. A diagram for number 23. Okay, let me sketch it. The diagram is under a plane mirror. This is a plane mirror. That's the back side, and this is the coated side. So in the plane mirror, we are having a point object. There's a point object, and an object is there, a point object. So a ray of light, a point object. So a ray of light incident this way and is reflected this way. So a ray of light incident that way and is reflected that in that particular direction. So this is the normal. We put normal. Okay. Then another ray comes from the point object. Another ray comes from point object. Incident, and then is reflected. is reflected. And this is normal for that one. That's normal for that one. Okay, so we're told that this one is first normal, this is second normal, n prime. Okay, and we are told that this point object is E, represented by letter E. So the incident ray for the first one, incident ray, the reflected ray is represented by incident ray, represented by Q. Then for the second incident ray, reflected ray is represented by F. And they said the point here, the point of incidence here is point A, and the point of incidence here is point B. Okay, and then we have this. Okay, normal to the mirror. You know, it is a plane mirror, and a plane mirror will give you the same the distance between the objects, the distance of the object to the mirror and the distance of the image to the mirror is the same. Okay, I mean they are the same. So we have from here, we have this. Continue this. We have this reflected ray also. According to the diagram, you extrapolate the reflected ray. I think you trace the reflected ray backward and represented by C. Okay, so this is the object, this is the word image. And characteristics of a plane mirror, characteristics of the image formed by a plane mirror. Number one, the image is virtual. Number two, the image is upright or erect, standing upright, it's not inverted. Are you there? It's standing upright. Number three is laterally inverted. Laterally inverted, as in if you are facing your plane mirror like this, if you are facing it this way, are you there? If you are facing it this way with your palm, are you there? So if you're facing it the other way, you're seeing the back side. So that is laterally inverted, side inversion, not top or bottom inversion, side inversion, lateral. Okay, then distance of the object to the mirror and distance of the image to the mirror, they are the same thing. They are the same. Okay, so now they said we just look at, which of the following is wrong. The figure below illustrates formation of an image of an object E by a plane mirror. This is a plane mirror. Which of the following statement is not correct about the figure? Which of the following is not correct about the figure? Option A, angle EAN, this is our A, this is our B. Angle EAN at this point, angle EAN, that point, is equal to NAQ. That's this point. So of course, for reflection, for angle of incident is equal to the angle of reflection. Angle of incident is this, angle of reflection is it. This is incident ray and this is reflected ray. So this angle is angle of incidence, this angle is angle of reflection. So they are equal. That is one of the laws of reflection. So that one is correct. Option A is correct. We're looking for the one that is wrong. Option B, BF is a reflected ray. BF. Yes, BF is a reflected ray of this incident ray. EB is incident ray. BF is reflected ray. Option B is correct. Option C, EA is an incident ray. EA, yes, EA is an incident ray. Then D, option D, EAQ. Let's look at EAQ. EAQ. That means the whole of this angle, EAQ, has the same value as EBF. That means the whole of this angle. Are they the same? No, they cannot be the same, because the angle of incidence here can be 30 degrees. Can be 30 degrees. Are you there? The angle of incidence here can be 30 degrees. If the angle of incidence is 30 degrees, the angle of reflection here will also be 30 degrees. 30 plus 30, that's 60. Now, the angle of incidence ray will not be 30 degrees. It can be 50 degrees because it's wider than this. Are you there? Because this angle here is wider than this. The angle of incidence here can be 50 degrees. If the angle of incidence here is 50 degrees, the angle of reflection here will also be 50 degrees. 50 plus 50, 100 degrees. So 100 degrees is more than 60 degrees. So they cannot be the same. That one is wrong. So option E. Option D is the correct answer. Let's look at option E. Option E says the image will be laterally inverted. Yes, the image will be laterally inverted. If you are facing it north, it faces you what? If the object is northward, the image will be southward. If the object is eastward, the image will be westward. So facing like that. So option D is wrong. So that is our answer. Number 23, D. 23, D. 24. Number 24. An object is placed between the focal length. An object is placed between the focal length and the center of curvature of a concave mirror. For a concave mirror, this is a concave mirror like this. Okay, and this is the principal axis. That's the principal axis. This is the focus, and this is the center of curvature. Okay, C is the center of curvature. This is the focus. Right there. So, and this is the pole. Okay, this is the pole. This is the pole. This is the focus. This is center of curvature. So now, if the object is beyond C, are you there? What are the characteristics of the image? Are you there? So if the object is beyond C, at the back of C, the image will be real, inverted, and diminished. Real, inverted, smaller. Real, inverted, smaller. When the object is at C, it will still be real, it will still be inverted, but it will be the same size. The same size as the size of the object, the same size. So if the object between C and F, if the object is between C and F, that is here. Are you there? Either between C and F, the image will still be real, will still be inverted, but it will be bigger. You can use another word, magnified. It will be bigger. Real, inverted, bigger. If the object is at F, the image will form at infinity. It will form at infinity. Are you there? At infinity. So if the object is between F and P, the image will not, all this characteristics is real, inverted. Real, inverted. So, but if the object is between F and P, the image will not be real again. It will be virtual. And once it is virtual, it will not be erect. It will not be inverted again. It will be what? Erect, or you say upright. Then it will still be magnified, bigger. Okay. So you now said an object is placed between focal length F and the center of curvature C. The object is between focal length F and center of curvature C. Yeah. So let me remove this. So the object is between C and F. Okay. Where is the image formed and what is the nature? So let me also state the position. If the object is here, are you there? If the object is beyond C, the image will form between C and F. If the object is beyond C, the image will form between C and F. Apart from the characteristics of the image, I'm talking about the position now. For position, if the object is beyond C, the image will form between C and F. But if the object is between C and F, according to the question, it will be at the back. The image will form at the back of C. The image will form beyond C, at the back of C. So, question: an object is placed between the focal length F and the center of curvature C. Focal length F, center of curvature C. That's the object. Where is the image? Where is the image formed? Where is the image formed? Are you there? Where is the image formed? The image will form beyond C, at the back of C. And what is its nature? The nature means the characteristics. It will be real, inverted, and magnified. So let's look at the option. Option A. That is the image you form at C. The image you form at C, and the characteristics will be real, inverted, and magnified. All those ones are wrong. The image will not be formed at C. Option B. The image will form behind mirror. Yes. It's formed behind mirror. Yes. But the nature, virtual, erect, and magnified. Wrong. It's not virtual. It's not erect. Option C. The image will form between F and C. No. The image will not be formed between F and C. It's the object that is at between F and C. The image will not be formed between F and C. That's wrong. Option D. The image will form beyond C. Yes, the image will form beyond C. And the nature, it will be real. It will be real, correct. It will be erect. No, it will not be erect. It will not be erect. That one is wrong. Now, option E. The image will form beyond C. Yes, at the back of C. It will be real, inverted, and magnified. Correct. So option E is correct. Option E for number 24. Option E is the correct answer. Now 25. Let's go to number 25. For 25, kind of a calculation. 25. The image formed by a converging lens. A converging lens. Are you there? So a converging lens is same thing as a convex lens. A converging lens is same thing as a convex lens, and the focal length is positive. The focal length is positive. If it is diverging lens, otherwise known as concave lens, the focal length is negative. So the image formed by a converging lens is upright and magnified 5 times. Calculate its distance if the focal length of the lens is 20 centimeters. I repeat, the image formed by a converging lens is upright and magnified 5 times. We have the formula you're going to use here is the lens formula. 1 over F equals to 1 over V plus 1 over U. That's one formula. Another formula is M equals to V over U. So M is the magnification, and V is the image distance, U is the object distance. Okay? So image distance, object distance. V is image distance, U is the object distance. Are you there? So at the same time, we can say magnification is image height over object height. Magnification can also mean image height over what? Object height. So now F is the focal length, V is the image distance, U is the object distance. Now said the image formed by a converging lens is upright and magnified 5 times. That means our magnification M is 5. Let me come here. That means M is 5. So M is 5. So the image formed by a converging lens is upright and magnified 5 times. That means when you substitute into this particular M equal to V over U, let's substitute 5 into this. 5 equals to V over U. When you make V, when you come to multiply, you have V equals to 5U. So that is one particular part of the solution. V is equal to 5U. So that the image is bigger, 5 times the size of the object. Calculate its distance if the focal length of the lens is 20 centimeter. Focal length is F. F is 20 centimeters. Okay, so for a converging lens, the F is positive. So you don't put minus there because it is positive. Are you there? But if it is a diverging lens, you put minus. Okay, so let's go back and substitute the values. So 1 over F is what? 20 equals to 1 over V. So V is 5U. V is 5U plus 1 over U. So 1 over 20 equals to LCM is what? 5U. Okay, 5U divided by 5U, that is 1, plus 5U divided by U, that is what? 5. Okay, so we have 1 over 20 equals to 6 over 5U. So making you the subject, when you cross multiply, you have U equals to 120 over 5. Okay, you have U as what? 120 over 5. So now 120 divided by 5 will give you 24. So our U is 24 centimeter. U is 24 centimeter. Though 24 is in the option, are you there? But that's not the final answer. 24 is an option, but that's not the correct answer. That's not the final answer. You have to continue from here. It said the image formed by a converging lens is upright and magnified 5 times. Calculate its distance. Calculate its distance. That means they are still referring to the image. Calculate its distance. That means they are still referring to the image that they started with. If the focal length of the lens is 20 centimeters, calculate its distance. So we are looking for image distance. Image distance from here, we said V is equals to 5U. So V equals to 5U. So that means V equals to 5 times U, 24. And 5 times 24 times 5 is what? 24 times 5 is 120. That's 120 centimeters. So this is final answer. If you stop at 24, object distance, you see the answer, that 24 is in the option, but that's not the correct answer. Okay, so we have option A, 16 centimeter, option B, 20 centimeter, option C, 24 centimeter, option D, 100 centimeter, option E, 120 centimeter. So the correct answer is what? 120 centimeter. That's option E, number 25. Now let's go to number 26. Number 26. Number 26. Number 26 says, which of the following statement is correct about gamma rays and X-rays? Which of the following statement is correct about gamma rays and X-rays? Let me clean the board a little bit. About gamma rays and X-rays. Which of the following statement is correct about gamma rays and X-rays? Okay. Now I know that before I've given you reverse. That's an acronym, reverse. Okay. So radio wave, infrared ray, visible light, ultraviolet ray, X-ray, and what? Gamma rays. So X-rays and gamma rays, they are all these ones. They are electromagnetic waves. Okay. So they said they are option A. They said which of the following statement is correct about gamma rays and X-rays? Okay. Option A, their method of detection is the same. Their method of detection is not the same because gamma ray is obtained from the disintegration of a radioactive element. The dissociation of radioactive elements. Are you there? So, and radiations, when a radioactive element like uranium disintegrates, it emits 3 types of radiations: gamma rays, alpha particles, and beta particles. All these radiations, these 3 radiations, they can be detected by maybe the Diamolar counter, scintillation counter, electron chamber. Do you understand? But X-ray cannot. X-ray is not obtained from the disintegration of radioactive element, so they don't have the same method of what? Detection. Option B, their mode of production is the same. For X-rays and gamma rays, their mode of production is not the same. X-rays is obtained or is produced from X-ray tube. X-ray is obtained or produced from X-ray tube, but gamma rays are obtained from the disintegration, spontaneous disintegration of a radioactive element. Well, option B is wrong. Option C, they have the same frequency. No, look at it. From R to G, the frequency increases. From R to G, the frequency increases. Are you there? And from R to G, the wavelength decreases. From R to G, from radio wave to gamma ray, the frequency increases. Are you there? Now, from R to G also, the wavelength decreases. That means gamma ray has the shortest wavelength, while radio wave has the longest wavelength. This one has the shortest wavelength, this one has the longest wavelength. Then for frequency, that means if frequency increases in this order, that means gamma ray has the highest frequency, while radio wave has the lowest frequency. So let's now compare S and G in terms of frequency. So this one has a higher frequency than S3. Gamma ray has a higher frequency than S3. So that means option C is wrong. Option D, they have the same uses. Yes, they are radiations, but they have high penetrating power. They have high penetrating power. Okay, gamma rays are used in gamma rays is used in medicine, either for the treatment of cancerous growths, either for the treatment of cancer. We can also use X-ray for that. Since they have high penetrating power, you can use them to review the internal structure of luggages or baggages in airports, to review what is inside a particular bag, either. So because they can penetrate a thick material. Okay, they can penetrate. So, and then you can also use them to review the internal structure of animals, of human being. You got to review the biochemical system, either to see if it's a small boy swallows a pin, and before they will go into operation, they will have to look at the position of the pin inside the ball. So you can use X-ray or gamma ray to review that. So option E, they have the same wavelength. No, they don't have the same wavelength. The wavelength decreases from radio wave to gamma ray. The wavelength decreases. Gamma ray has the shortest wavelength. So the wavelength of gamma ray is smaller than the wavelength of X-ray. So the correct option is D. Option D. They have the same uses. Okay. Number 27. That's number 26. Now number 27. Now, which part of the human eye performs the same function as the diaphragm of a camera? Which part of the human eye performs the same function as the diaphragm of a camera? No, we have, there are similarities between the camera and the human eye. There are similarities. Okay. Now we have option A, we have blind spot. Option B, cornea. Option C, iris. Option D, pupil. Option E, retina. So when you look at iris controls the amount of light that enters the eyes. Iris controls the amount of light that enters the eyes. Either camera, the diaphragm of a camera controls the amount of light that enters into the camera also. So the diaphragm of the camera controls the amount of light that enters. So the iris in human eye is the same. The iris in human eye is the same as the diaphragm in a camera. Now the pupil, that's dots on top of that black pigment. So the pupil is the small O. That small O in the eye. So is that small O that allows light to pass through. That small O allows light to pass through. So that small O, which is pupil, is the same, which is pupil. So that pupil controls that pupil allows, is that small O through which light enters. Either is that small O through which light enters. Retina is the sensitive part of the eye. The sensitive part of the eye. Retina is just like the film or screen, the film in the camera. Either the film in the camera. So the pupil is the same thing as the aperture in the camera. The pupil is the same thing as aperture in camera. The iris is the same thing as diaphragm. The iris in human eye is the same thing as diaphragm in camera. The pupil in human eye is the same thing as aperture in camera. The retina in human eye, which is the light sensitive part, is the same thing as the film in the camera. So the correct option is what? Option C, iris. So iris is the same thing as diaphragm. So don't forget that the image formed by camera and then human eye is real and inverted. Real and inverted. So it is the brain that we interpret as being erect. So number 27, that's option C is the correct answer. Option C is the correct answer. Number 28 now. 28 is a calculation question. 28 now. Formula 28, a string of mass per unit length, x kilogram per meter. A string of mass per unit length, s kilogram per meter. Let's represent it by mole. So that is s kilogram per meter. This is mass per unit length. I represent this mole, this symbol, with mass, by mass per unit length. Okay, so the mole is given as x kilogram per meter. A string of mass per unit length, this is under a tension of 20 Newton. Under a tension is capital letter T, equals to 20 newtons. Tension is capital letter T, that's 20 newtons. So if the speed of the waveform is 31.62 meter per second, speed, so letter V, that's 31.62 meters per second. That's the speed given. What is the value of x? So we're looking for x. S is unknown now. Okay, what's the value of x? Said a string of mass per unit length, x kilogram per meter, is under a tension of 20 newtons. If the speed of the wave formed is 31.62 meters per second, what is the value of x? So the suitable formula for this, under string, the tension in a string, the string of a jitter, the tension on it. We're talking about, so the string of a jitter. So when you plug it, are you there? When you plug it, are you there? There is tension in it. Okay, the formula to calculate the tension in the string of any string instrument, we have F is equals to 1/2L square root tension over mole. I represent mole by mass per unit length. This mole is a mass per unit length. Are you there? If you are given mass in the question, I are given length in the question, so you divide the mass. Say mass divided by length. Mass divided by length will not give you this mole. Will not give you this particular symbol, mass per unit length. Okay, so now you can see that if you are looking for T, which is the tension, we have mole, which we are looking for, which is x. We don't have length, we don't have frequency. We don't have length, we don't have frequency. We are not given length, we are not given frequency. We are given V. Are you there? So we now go back to we have closed pipe and open pipe. Closed pipe and open pipe under sound waves. Are you there? So for open pipe, we are going to use open pipe for a string. Open pipe harmonics. Open pipe harmonics. For open pipe, we have, for the harmonics of open pipe, the harmonics of open pipe. Okay, you use the harmonics of open pipes for strings. Are you there? So we have F naught, 2 F naught, 3 F naught, 4 F naught. Continue. They are just integers. It continues. Okay, they are just integers. Are you there? So this is the first harmonic. This is second harmonic. This is the third harmonic. This is the fourth harmonic. First harmonic, second harmonic, third harmonic, fourth harmonic. Continue. But this is the first overtone. First overtone, second overtone, third overtone. First overtone, second overtone, third overtone. But first harmonic, second harmonic, third harmonic, fourth harmonic. So the first overtone starts from the first overtone is the second harmonic. So this F naught, and they also go with their own formulas also. We have, for this one, we have L equals to half lambda. Here we have L equals to 2/2 lambda, half lambda. You just adding 1 to the numerator. The denominator remains 2. Automatically. So the numerator, you'll be adding 1 to the numerator. So 1/2. Add 1 to the numerator, 2/2. For this third one, L equals to, add 1 to the numerator, that's 3/2 lambda. For the fourth one, L equals to, add 1 to the numerator, that is 4/2 lambda. Okay, lambda. Okay, like that. So We are going to use the fundamental frequency, this first one. Okay, since we're not told first harmonic, we're not told second harmonic, first harmonic, third harmonic, fourth harmonic, or first overtone, second overtone, third overtone. So you use the fundamental harmonic, which is the first harmonic. So from here we can see that L equals to half lambda. L equals to half lambda. So we are going to replace. We want to replace here. We want to replace L equals to F lambda, and then if you replace your L, you can see that we can have L is half lambda here. If I make let me make L is already half lambda, I can come here and substitute. I can come here and substitute in the formula. I have F equals to 1/2 times, what is my L? My L is half lambda. Okay, that's my L, half lambda. So 2 cancel 2. Okay, let me repeat this. Tension over mass per unit length. Okay, so 2 cancel 2. Then I have F equals to 1/2 cancel 2. I have 1 over lambda left here. Then tension over mass per unit length. Okay, now let me multiply both sides by lambda. Multiply both sides by lambda. So we have F lambda equals to tension over mass per unit length. Okay, so I have F lambda equals to tension. Multiply both sides by lambda. I want the lambda to come here. When you multiply both sides by lambda, this one times lambda will cancel lambda. Are you there? Then this one times lambda is this. That's the meaning of multiply both sides by what? Lambda. So F lambda equals to square root of tension over mass per unit length. And don't forget that we know that V equals to F lambda. V equals to F lambda. Lambda is wavelength, F is frequency, and V is speed. Okay, so V is equal to F lambda. So that means we are going to replace this F lambda with V. So that means V equals to square root tension over mass per unit length. So V equals to tension over mass per unit length. Okay, so now this is the formula we are going to use. This is the formula that we are going to use. V equals to square root of tension over mass per unit length. So let me substitute from here and I will come down. Okay, what's our V? Our V is given as 31.62 equals to square root tension. What's our tension? Our tension is 20 over our mole. Our mole here, mass per unit length is X. So we should take it as X. So how do you find X there? We square both sides in order to remove the square root. Square both sides in order to remove the square root. Square both sides. 31.62 squares. 31, now relatively 1000. 31.62 squared. Square it. Square both sides. That was giving us 999.82. Okay, that the square of this equals to, when you square this like this, you square this like this. Right there. So once you square the other side, the square remove the square root. The square remove the square root. Right there. You left with 20 over x. So the square remove the square root. So we left with 20 over x. So cross multiply, we have x equals to 20 over 999.82. Okay, so let's divide that. That's 20 divided by 999.82. That one is giving us 0.02 mass per unit length. That's kilogram per meter. 0.02. So let's look at the options. 0.02. Okay. Number 28. Option A, 5 times 10 raised by 3. Option B, 2 times 10 raised by minus 2. And that's our answer. 2 times 10 to the minus 2 is same thing as 0.02. Okay, so 2 times 10 to the minus 2 is same thing as 0.02. So option C is wrong, option D is wrong, option C is 3 times 10 to the minus 3, option D is 4 times 10 to the minus 5, option E is 6 times 10 to the minus 5. So option B is the correct answer, 2 times 10 to the minus 2 kilograms per meter. Number 20. Let's go to number 29. Number 29. Okay, let's read the question first. 29. The air column in an open pipe. Oh, I've said something about open pipe before. The air column in an open pipe of length 10 centimeters is set into vibration. The air column in an open pipe of length 10 centimeters is set into vibration. Calculate. You can see open pipe like flute instrument, musical instrument, flute. Okay, both ends. Okay, so you can see it like that. So the air column in an open pipe of length 10 centimeters is set into vibration. Calculate the frequency of the second overtone. Oh, frequency of the second overtone. We are given velocity of sound in air as 340 meters per second. I've mentioned something about harmonics and overtone. So let's clean this and leave those harmonics I've written before. Okay, let me write. So harmonics for open pipe. For open pipe, the harmonics are F0, 2F0, 3F0, 4F0, continue. And the length is L equals to 1/2 lambda. For the second one, L equals to, just adding 1 to the numerator, 2/2 lambda. For the third one, for corresponding to 3F0, let me put R so that you see very well. For this, you use L equals to half lambda. Are you there? For this, alongside, you use L equals to 2/2 lambda. For this, you use L equals to 3/2 lambda. Be adding 1 to the numerator. Leave the denominator constant. Now, for this, you have L equals to 4/2 lambda, like that. Okay? Now, for open pipe. For closed pipe, you start with L. For closed pipe, you start with L. Okay, let me just write closed pipe. We don't need closed pipe now, but let me just write it for closed pipe. And then for closed pipe, it will be the first fundamental frequency either is in odd numbers. That's F0, 3F0, 5F0, 7F0. That is odd numbers for closed pipe, the integers for open pipe. So the corresponding length for this, L equals to 1/4 lambda. 1/4 lambda. Are you there? For this, you'll be adding 2 to the numerator. Are you there? You're adding 2 to the numerator. You leave the denominator constant. So L will be 3/4 lambda for this. When you add 2 to this one, now add 2 to this one. L here will be 3 plus 2, 5/4 lambda, like that for closed pipe. But we are talking about open pipe here. Let's go with open pipe. It said the air column in an open pipe of length 10 centimeters. So for open pipe, 10 centimeters, that means the L is what? 10 centimeters. Is set into vibration. Calculate the frequency of the second overtone. Frequency of second overtone. We are given V, velocity of sound in air, as 340 meters per second. Convert this one to meter. You have to convert it to meter. It must be in meter. So that's 10/100. 10/100. And that's 0.1 meters. Okay? So we are looking for frequency of the second overtone. Let's go to the open pipe. For open pipe, this is the first harmonic, second harmonic, third harmonic, fourth harmonic. Then for closed pipe, also first harmonic, second harmonic, third harmonic, fourth harmonic. But overtone, we start from the second phase, second one, overtone. So this is the first overtone for open pipe. This is the first overtone, and this is the second overtone. So we are looking for second overtone. Second overtone is 3 F notes. Second overtone. Second overtone. Overtone is what? 3 F notes. That's second overtone is 3 F notes. So we have to go and get our F naught. F naught is fundamental frequency. When we get F naught, we now come back and multiply it by 3 to get the frequency of second overtone. Let's go and get F naught first. Are you there? Now, we are given length and V. How can you convert that? First and foremost, let's go back to because the formula to calculate our F naught is V equals to F lambda. Okay, so we know our V. We know V. We are looking for F. Are you there? But we don't know lambda. We don't know the wavelength. We are not given the wavelength. But you can get wavelength from all this. You can get wavelength from here. Which one are you going to use? Is it this? L is equal to half lambda, or L is equal to 2 over 2 lambda, or L is equal to 3 over 2 lambda? We are going to use L is equal to 3 over 2 lambda because it's this one that corresponds to the second overtone. It's this one that corresponds to the second overtone. L equals to 3 over 2 lambda. Okay, so L equals to 3 over 2 lambda. Okay, what's our L? 0.1. Then 3 over 2 is 1.5 when you divide it. Lambda. So 3 over 2 is 1.5 when you divide it. So we have our wavelength. So make reference to the formula. We have wavelength equals to 0.1 over 1.5. That's our wavelength. So 0.1 over 1.5. 0.1 divided by 1.5 equals to 0.067. 0.067. That's 0.067 meters. That's our wavelength. 0.067 meters. That's our wavelength. So we now come back to V is equal to F lambda. V equals to F lambda. What's our V? Our V is 340. What's our F? We're looking for F. Okay. Then multiplied by wavelength. Wavelength is 0.067. 0.07. So make F the subject. So F equals to 340 over 0.067. What would that one give us? What would that one give us? We're having 340 divided by 0.067 equals to so we're having, this one is giving us roughly F equals to 5074. You have 5074, right? 5074 0.63 x. Okay. Now they said calculate the frequency of the second overtone. This is the first overtone and this second overtone, and this is half lambda, 2 over 2 lambda, and 3 over 2 lambda. So now we now go back and multiply by 3. We now go back and multiply by 3. But for the fact that we have used this 3 over 2 lambda, that 3 over 2 lambda has catered for this 3. This 3 over 2 lambda catered for this 3. Are you there? So we don't need to multiply by 3 again. Okay, sorry for that. So this 3 now, this 3 denominator corresponds to this 3. 3 denominator corresponds to this. So we don't need to, because this goes with this. Okay, so the 3 here is the 3 here as numerator. Okay, so we don't need, haven't gotten this, so we don't need to go and multiply by 3 again. Are you there? The same thing for this 4 F naught corresponds to 4 over 2 F naught. So we're looking for the frequency. You have this 4 as this 4. Are you there? This 4 as this 4. Okay. So 5074.63 arcs. As that is the final answer. So you need to go and multiply by 3 again, because this 3 here is already 3 here. The 2 here is already 2 at the numerator. The invisible 1 here is the 1 at the numerator here. The 4 here is the 4 at the numerator here. So when you correct this to the nearest 1000, when you correct this to the nearest 1000, you have F as 5100 arcs to the nearest 100. Sorry to say, to the nearest 100. Okay, you have 5100 arcs to the nearest hundreds. Okay, arcs approximately. So let's look at the option. We have 1700 arcs, 3400 arcs, 4400 arcs, 5100 arcs, and 6800 arcs. Right there. So our correct answer is 5100 arcs to the nearest 100. Okay, so F is equal to this. So number 29, option D, is the correct answer. Okay, I need to drink water. Water is life. Life is simple. Life is easy. Take it easy. Yeah. Okay. All is well. So let's go to the next number. Physics is interesting. That's my slogan. It's interesting. Look at the way I'm just breaking down everything for you bit by bit. Better understanding. All right, let's go to number 30. Number 30 says, a boy standing X meters. A boy standing X meters away from a wall. A boy standing X meters away from a wall claps his hands. And hears an echo. 3 seconds later. Determine the value of X. We have given the speed of sound in air as 330 meters per second. Echo is a reflection of sound waves from a plane surface. Echo is what? The reflection of sound wave from a plane surface when the source has died down. Echo is a reflection of sound waves from a plane surface when the source has died down. Are you there? When the source has been removed. Okay, and that one happens mostly in the auditorium. It happens in the auditorium. So when you speak, you hear your voice over and over. When you have stopped speaking, you'll be hearing your voice over and over. Okay, that's echo. And how in auditorium, how did they prevent this? They treat the walls with soft material, with soundproofed materials. The walls are treated with soundproofed materials that can absorb sound to avoid reflection, to avoid that echo. And you see that in some auditorium they put curtains, the line curtains on the wall, the curtains on the wall. So all those things are just to prevent echo from occurring. But this one is calculation. A boy standing, the formula to calculate, the formula to use in echo for the speed of sound, we know that V equals to distance over time. You're not going to use this formula. You're not going to use distance over time. You use 2D. The formula will be V equals to 2D over time. That's the formula for echo. Why are we using 2D? Are you there? The sound travels, it incidents, that's one distance, and it comes back, that's another distance. And that's why we are using 2D as the numerator. Okay, so you are going to use V equals to 2D over T. So we have been given speed. It says a boy standing X meters away from the wall. That's our distance. Our distance is X according to this particular question. So our distance is X. Our distance, the D is X meters given. Claps his hands and hears an echo 3 seconds later. Time is 3 seconds. Determine the value of S. The speed of sound in air is 330. speed is 330 meters per second. So let's substitute. Our v is 330 equals to 2. Our d is x over time. Time is 3. Cross multiply and make x the sub there. We have x equals to 330 times 3 over what? 2. At the end of the day, you have what? So that's 330 times 3 divided by 2. That gives us 495. That gives us 495 meters. Okay, 495 meters. Okay, look at the options. Option A 110, option B 333, option C 495, option D 520, option E 990. So the correct option is what? Option C, 495 meters. That's number 30. So let's go to number 31. Number 31 is not the calculation question. 31. The following are examples of fields. So these are examples of fields. Remember figure 1, they gave us electric field. Remember figure 2, we are given electrostatic. Remember figure 3, we are given gravitational field. Remember figure 4, we are given magnetic field. Okay, so these are the fields given. In which of the field is repulsion not experienced? In which of the field is repulsion not experienced? You know, we have attraction and repulsion. When you are talking about charges, we have positive charge and negative charge. So when there are bound to be attraction, if a positive charge comes across a negative charge, and there will be repulsion when we have positive charge and positive charge, or we have negative charge and negative charge, there will be repulsion. So for charges, but for masses, we don't have positive mass and we don't have negative mass. We can't say the mass of a boy is minus 20 kilograms. So it's not feasible, it's not practicable, it doesn't exist. So now you use that idea to answer this. When you look at electric field has to do with charge, where we have positive charge and negative charge. We can have positive charge for attraction, positive charge and negative charge for attraction. We can have positive and positive repulsion. We can have negative and negative repulsion. So electric field has to do with charge. Electrostatic field also has to do with charge. Electrostatic field also has to do with charge, and that's why when you rub your pen against your air vigorously and bring it very close to a thin paper, there will be attraction because of opposite charges, positive and negative. Are you there? Then gravitational field. Gravitational field has to do with only mass. Okay, so only mass. So you can't have attraction and you can't have repulsion when it comes to masses. Okay, so now that means option 3 is the correct answer. Option 4, magnetic field. Magnetic field, we have north pole. For a magnet, we have north pole and we have south pole. Are you there? North pole and south pole. So when we have north pole and south pole, there will be attraction. Are you there? That is, like poles repel, unlike poles attract. When you have north pole and north pole, they repel. South pole and south pole, they repel. And we have north pole and south pole, they attract. So like poles repel, unlike poles attract. We also have like charges repel, unlike charges attract. So it's only gravitational field that has nothing to do with repulsion or attraction, because it has to do with what? Mass of a body, not the charge of a body. So option A, 1 only. They said, in which of the fields is repulsion not experienced? Option A, 1 only. Roman figure 1 only. Option B, Roman figure 2 only. Option C, Roman figure 3 only. Option D, Roman figure 4 only. Option E, 2 and 3 only. So the correct option is option C, 3 only. 3 only. This one, professional. So number 31, the correct option is what? Option C. Now number 32. 32 now. The diagram below, let me sketch the diagram. Let me sketch the diagram. Let me sketch the diagram. Okay, we have the diagram in form of F. F as a planet. Okay, that's longitude. We're having latitude. They give us latitude in that way. They give us a point here as Roman figure 3. So we are given a point here as Roman figure 1. We are given a point here as Roman figure 2. We are given a point here as Roman figure 4. We are given a point here as Roman figure 5. So they just said that the diagram below represents the Earth. This is the Earth, showing the equator. Showing the equator. This is equator. Showing the equator. This is equator, and then the pole. This is the pole. These are the poles. North Pole and South Pole. Then and other points. These are the points. Other points and other points. At which of the points labeled, 1, 2, 3, 4, and 5 is the acceleration of free fall due to gravity greatest? Is the acceleration of free fall due to gravity greatest? Where is the acceleration of free fall greatest here? This is the Earth's surface. This is Earth as a planet. This is the equator. This is the equator, and this point is a pole. This is another pole, North Pole and South Pole. Now we know that at the equator, acceleration to gravity G, acceleration to gravity is roughly 9.83 meters per second square at the equator. At this point, let me write G here. So at equator, at this point, G is roughly 9.83 meters per second square. That's at equator. 9.78 meter per second square. At the equator, acceleration to gravity G is 9.78 meters per second square. So at the pole, this is the pole. Our G is 9.83 meters per second square. Acceleration due to gravity at the pole is approximately 9.83 meters per second square. At the equator is 9.78 meters per second square. So look at it now. So as we move from the equator to the pole, the value of acceleration to the gravity increases. It increases. By the time you calculate it, it increases by roughly 0.5%. As you move from the equator to the pole, the value of acceleration to gravity increases by 0.5%, roughly. So 9.78 here, 9.83 here. So this is the pole where the acceleration to gravity is what? Greatest or highest. Okay. So let's look at the option. They said diagram below shows the Earth shows the Earth showing the equator, the pole, and other points. At which of the point labeled 1, 2, 3, 4, and 5 is the acceleration of free fall due to gravity greatest? That is at the pole, which is at this particular V. Roman figure V. Roman figure V. Roman figure 5. Are you there? So option A, Roman figure 1. Option B, Roman figure 2. Option C, Roman figure 3. Option D, Roman figure 4. Option E, Roman figure 5. That's V. So our correct answer for number 32 is option E. That's number 32. Option E. Don't forget. Now 33. 33 is not a calculation question, but it doesn't need to sketch if need be. Okay. 33. Which of the following statement is correct about electric lines of force? Electric lines of force. Are you there? So electric lines of force. Okay. Electric lines of force are imaginary lines. Are you there? Along which a free positive charge will tend to move. A free positive charge will tend to move. Okay, so this one, they want to test us on the characteristics of electric lines of force. Are you there? So they say, which of the following statement is correct about electric lines of force? Option A, the closer, these are the electric lines. If I have positive charge here, the electric line of force will moving out. We move out. Electric line of force are directed outward for a positively charged body. For a negatively charged body, electric line of force enters. Look at the arrows. Enters. Okay, it enters. So let's look at option A. Which one is correct? Option A, the closer the lines, the weaker the electric field. No. Option A, the closer the lines, the weaker the electric field. No. The closer the lines, the stronger is the electric field. The closer, when the lines of force are very close. Look at this one now. If I have this and I have this, these lines of force and these three lines very close to each other. So this one is weaker because we have more space. This one is stronger. Do you understand? He said, united we stand, divided we fall. When you have enough space, that means you are dividing yourselves. Are you there? You can't do exploit. But when you come together, you put brains together, you can change the world. So when they are when the line of force are very close together, are you there? The strength is high. So option A, the closer the lines, the weaker the electric field. That is wrong. The closer the lines, the stronger the electric field. Option B, arrows on the lines indicate the strength of the field. So arrows on the lines indicate the direction of the field. Arrows on the lines indicate the directions of the field. For positively charged body, the arrows are pointing outward. For negatively charged body, the arrows are entering. They are entering. Okay, so that one is wrong. Now option C, line starts at negative charge and end on positive charge. No, the line starts on positive charge and enters negative charge. The line starts on positive charge and ends on negative charge. That was equally wrong. Now option D, lines are straight and parallel in a uniform field. Oh, for a uniform field, the lines are straight and also parallel. For example, let's look at the if you look at the field of the earth. The field of the earth, they are straight lines, equally spaced and parallel. Okay, so lines are, for a uniform field, the lines are parallel and they are what? Uniform. Lines are parallel and what? Uniform. Equally spaced and equally spaced. You can't just catch any, they must have the same space, equal spacing. So when you see the word uniform, the lines are parallel and they are straight for any uniform field. Now option D is correct. Let's just look at option E. Number of the lines is inversely proportional to the magnitude of charges present. No. The higher the number of lines, the higher the strength, the higher the magnitude. The higher the number of lines, the higher the strength, the higher one. So option E is wrong. So option D is the correct option. But I think option D correct. Now let's go on to 34. 34 now. 34 is calculation. Is a calculation question. 34. A galvanometer of resistance 6 ohms gives a full-scale deflection. A galvanometer of resistance 6 ohms gives a full-scale deflection. A galvanometer of resistance 6 ohms gives a full-scale deflection when a current of 20 milliamperes passes through it. Calculate the value of resistance required to make it capable of measuring 1.5 amperes. I repeat the question. A galvanometer of resistance 6 ohms gives a full-scale deflection when a current of 20 milliamperes passes through it. Calculate the value of resistance required to make it capable of measuring 1.5 amperes. This one is conversion of a galvanometer to an ammeter. A galvanometer can measure a very small current, while an ammeter can measure a relatively large current. So an ammeter can measure 1.5 ampere, but a galvanometer may not be able to measure up to that 1.5 amperes. It can measure up to that 1.5 amperes. So now I want to use that same galvanometer to measure 1.5 amperes. If you connect it directly like that, it will blow, it will burn. The galvanometer will burn. So you have to connect a resistor. It is that resistor that will lower the current. You have to connect a resistor to the galvanometer. Are you there? So you have to connect a low resistance in parallel to the galvanometer. You have to connect a low resistance in parallel to the what? Galvanometer. And the low resistance is known as shunt. Is known as shunt. So we have, let us say we have the galvanometer this way. That's what this is the galvanometer. The scale, this is the galvanometer. It is deflection. Let's say this galvanometer. The internal resistance. Let us say this is the internal resistance of the galvanometer. Because that's our resistance. Are you there? So we now come and convert and connect it to another resistance in parallel. Another resistance in parallel. Okay, let me bring it this way. You connect another resistance in parallel to this. Okay, so you have your battery. Okay, so you want to measure this. 1.5 amperes is coming, enters. 1.5 amperes. 1.5 amperes. Look at the arrow entering. So, and this one is the whole of the galvanometer. This one is the internal resistance, the resistance of the galvanometer. So they are in parallel like this. So a galvanometer of resistance 6 ohms. Resistance of the galvanometer is 6 ohms here. 6 ohms. I'm using R, capital letter R, subscript small letter G as resistance of the galvanometer. Capital letter R, subscript small letter G as resistance of the galvanometer. A galvanometer of resistance 6 ohms gives a full scale deflection when a current of 20 milliamperes. That's the maximum current that the current can measure. The maximum current that the galvanometer can measure is 20 milliamperes. Let me write it as parameters. Resistance of the galvanometer is 6 ohms. Then current of the galvanometer. I'm using capital letter I, subscript small letter G as the current at the current of the galvanometer equals to 20 milliamperes. 20 milliamperes. 20 milliamperes. So we have to convert milliamperes to amperes by dividing by 1000. 20 over 1000. This is that 20 milliampere is the maximum current that the galvanometer can measure. So when a current that is more than 20 milliamperes enters, it burns. And if you have to use it to measure a current of 1.5 amperes, so we have to like connect a low resistance shunt in parallel. So 20 over 1000, and that gives us this calculation, that's 0.02 amperes. That's the current galvanometer current. Now, so they now said calculate the value of the resistance required to make it capable of measuring 1.5 amperes. So this is the resistance we are looking for. So that's low resistance, otherwise known as shunt. Shunt. Let me use R subscript X to represent that. That is shunt resistance. R capital letter R of S represent that. So capital letter R subscript S is what we're looking for. That's the shunt, which is the low resistance. Now, there's one thing you have to take note here. You can't say that 1.5 amperes is the current of the shunt. No. You know, when resistors, this resistor of the galvanometer, which is the internal resistance of the galvanometer, and the shunt they are in parallel. They are in parallel. So when resistors are connected in parallel, they have different currents. They have different currents, but the same voltage. When resistors are connected in parallel, they have different current but the same voltage. That is, the current of resistance of this resistance is different from the current of this resistance. So that means the current that is coming, which is 1.5 amperes, they are going to share it. That 1.5 amperes current that is coming, they will share it. Are you there? They have to share it. So in such a way that the galvanometer has its own current already. The maximum current that the galvanometer can measure is 0.02 amperes. Are you there? Which is the one for the resistance of the galvanometer. Are you there? So the current of the shunts, the current of this one, are you there, will now be we subtracting the maximum current of the galvanometer from the incoming current 1.5. The current of the shunts, are you there, which are represented by I subscript X, will now be the current that is coming that I want to measure 1.5 minus the maximum current of the galvanometer, which cannot be exceeded, is 0.02. So that is the current of the shunts. So we now have 1.5 minus 0.02. That gives us 1.48. So 1.48 amperes. That is the current of the shunt of the low resistance. So having known that, let's now we have used the idea of these two resistors in parallel having different currents. Let's now use the second idea, that when they are in parallel, they have the same voltage. They have the same voltage. The voltage of the galvanometer is the same thing as the voltage of the shunts. Let's calculate the voltage of the galvanometer first. We know that V equals to IR. Are you there? From Ohm's law. So let me just substitute G. That is V substitute G, that's voltage of the galvanometer. I substitute G, current of the galvanometer. Then R substitute G, that is the resistance galvanometer. So let us substitute the values. Let's substitute now. Voltage of the galvanometer, we are looking for that. Voltage of the galvanometer, we are looking for that. Current of the galvanometer is what? Is 0.02. 0.02 multiplied by resistance of the galvanometer is here. That's 6. That's 6. So we have voltage of the galvanometer as 0.02 times 6. 0.02 times 6, and that's 0.12. So it's 0.12 volts, and that is the voltage of the galvanometer. Let's now calculate the voltage, formula for the voltage of the shunt, which is this low resistance. So we also know that V equals to IR. Are you there? So let's use substitute S to represent shunt. So voltage of the shunt, that is capital V substitute S. Voltage, current of the galvanometer, let's put substitute S, that is the current of the shunt. Then R substitute S, that is the resistance of the shunt. Are you there? Let's now substitute. The voltage of the shunt is the same as the voltage of the galvanometer. The voltage of the shunt is the same thing as the voltage of the galvanometer. Are you there? So because the two resistors are in parallel, and when they are in parallel, they have the same voltage. Voltage of the galvanometer is 0.12. So let's now take it as the voltage of the shunt. So Vs is now 0.12 equals to the current of the shunt. The current of the shunt, we have it here as 1.48. Current of the shunt is 1.48. That's 1.48. So multiplied by Rs. That's the shunt resistance. So making Rs the subject, R sub S equals to 0.12 over 1.48. So we have 0.12 divided by 1.48. 0.08. So shunt resistance is 0.08. You can put one like ohms. So that is the low resistance we are talking about. That is the resistance, or you call it shunt. Let's look at the options. Number 33. No, number 34. 34. It said a galvanometer of resistance 6 ohms gives a full-scale deflection when a current of 20 milliamperes passes through it. Calculate the value of resistance required to make it capable of measuring 1.5 amperes. Option A is 0.02 ohms. Option B is 0.08 ohms. Option C is 0.12 ohms. Option D 1.48 ohms. Option E 1.52 ohms. Can you see that some of the answers we got are there, but they're not defined. Like 0.12, we got 0.12 ohms, which is not the final answer. We got 1.48, which is not the final answer. But the final answer is 0.08, which is option B, is 0.08 ohms. So number 34, the correct answer is option B. Now number 35 now. Number 35 is also a calculation question. 35. You can play the video over and over for again, so if there's any calculation you still want to look at. So number 35, the balance length of a potentiometer wire. The balance length of a potentiometer wire connected to a cell of an unknown EMF is 9.0 centimeters. The balance length of a potentiometer wire connected to a cell of an unknown EMF is 90.0 centimeter. So when the cell is replaced by a Daniell cell of EMF 1.08 volts, the balance point is 64.8 centimeter. When a cell is replaced by a Daniell cell of EMF 1.08 volts, the balance point is 64.8 centimeter. Determine the value of the unknown EMF. This one is talking about potentiometer that can be used to compare the EMFs of two cells. That one of the uses of a potentiometer is to compare the EMF of two cells. So maybe we have this. There's a cell here connected to the potentiometer string, then connected to, maybe we have another cell here connected to a galvanometer, galvanometer G. Then we have our jockey. So this one is the string. This one is the string on the galvanometer. Are you there? This is the jockey. Are you there? Use jockey, the mouth of the crocodile clip, to be touching, or jockey itself to be touching this string on the potentiometer. So this is one cell. This is one cell that has its own EMF. Let's say E1. This is another cell that has its own EMF. Let's say E2. Are you there? When you are connecting it practically, the positive parts of this EMF must be connected to the positive parts of this EMF. The positive terminal of this cell must be connected to the positive terminal of the second cell for it to work, for the galvanometer to give you a normal deflection. But if you don't connect like that, the pointer of the galvanometer is moving to the back of zero. Even to the back of zero, where there are no numbers. Do you understand? So practically, you must connect it that way. So now, practically, we have known that the formula for calculating this on this particular potentiometer, when you're having two EMFs, is E1 over E2 equals to L1 over L2. Now this, the EMF is directly proportional to the length. The EMF is directly proportional to the length. So let's look at what we are given. So we are having to say the balance length of a potentiometer wire connected to a cell of an unknown EMF is, the balance length of a potentiometer wire connected to a cell of an unknown EMF is 90.0 cm. Unknown, let's the unknown EMF be E1. Are the E1? So the length of that one. Okay, let the unknown EMF be what? E1. Then E2. Now said when, let me list out the parameters so you can see. So for our E1 we don't know. Are you there? Then L1 is 90 centimeter. L1 is 90 centimeter. that the balance length of a potentiometer wire connected to a cell of an unknown EMF is 90.0 centimeter. Full stop. When a cell is replaced by a Daniell cell of EMF 1.08 volts, that's E2. E2 is 1.08 volts. That's E2, second cell. The balance point, when a cell is replaced by a Daniell cell of EMF 1.08 volt, the balance point is 64.8 centimeter. That means L2 is 64.8 centimeter. 64.8 centimeter. So the two lengths are in centimeters. So they need to convert to meter again. They will later cancel out when we substitute into the formula. Okay? Alright. So let's substitute into the formula. What's E1? E1 is what we are looking for. What's E2? E2 is 1.08 equals to L1. L1 is 90 over L2. S2 is 64.8. Is the taking? Is the taking? Oh yeah, cross multiply. Cross multiply and make E1 the substitute formula. That's E1 equals to 1.08 times 90 all over 64.8. 64. So let's divide that and let's see what that is going to give us right now. We have 1.08 multiplied by 90 equals to divided by 64.8, and that has given us 1.5 on dot. 1.5 on dot. E1 equals to 1.5 volts. Chineke. That means the cell is like a Leclanche cell. 1.5 volts. 1.5 volts. So let's look at the options. Option A, 2.58 volts. Option B, 1.50 volts. That's our answer. Option B. Let us read all that. Option C is 0.78 volts. Option D is 0.42 volts. Option E is 0.35 volts. Okay, so option B, 1.50 volt. That's the correct answer for number 35. Don't forget physics NECO 2021. Now number 36. 36 is not a calculation. The magnetic element at a place includes they give us number figure 1, 2, 3, and 4. They say the magnetic element at a place include number figure 1, angle of declination. Number figure 2, vertical component of the F magnetic field. Number figure 3, the angle of dip. Number figure 4, horizontal component of the F magnetic field. Are you there? You now said which of the statements above are correct. The magnetic elements, they are all of them. Magnetic elements are number 1, angle of declination. Angle of declination, another word is for angle of variation. Call it angle of declination or angle of variation. Are you there? Is the angle between the geographical meridian and the magnetic meridian. The angle between the geographical meridian and magnetic meridian. What do I mean by geographical meridian? The geographical north-south. Geographical north-south. Are you there? Why the magnetic meridian is the magnetic north-south. Magnetic north-south. Okay? Magnetic north-south. So in geography, you have your north this way. This is your north. This is your south. So this is the geographic meridian. Are you there? But when you carry a bar magnet like this, the bar magnet also has a north and south. When you carry like this and you suspend the bar magnet, it will come down. It will come to rest. It will not come down vertically like the north and south of geography. Are you there? It will bend a little bit like this. It will bend a little bit like this. North, south. This is for the magnets. Are you there? This is for normal map. Okay. So the angle between this is the geographical meridian, or you call it geographical north-south, and this is the magnetic meridian for magnet or magnetic north-south. So a bar magnet will always come to rest either in north-south magnetic direction. Okay. So when suspended, so this angle is called angle of declination. Angle between the geographic north-south and magnetic north-south. Or it's angle between geographic meridian and magnetic meridian. That's angle of declination. So that one is part of magnetic element. Now we go to vertical component of the Earth magnetic field. We have the Earth magnetic field. Earth magnetic field can be resolved into vertical component and what? Horizontal component. It can be resolved into vertical component, and one will be B sine theta, the other one will be B cos theta. Okay, so when we resolve it, so then we have so Roman figure 2 is correct. Vertical component of the Earth magnetic field. Roman figure 4, horizontal component of the Earth magnetic field is correct. Then Roman figure 3, the angle of dip. Angle of dip, DIP, is same thing as angle of inclination. Angle of dip or angle of inclination. Angle of dip or angle of inclination is the angle the Earth magnetic field mixed with the horizontal. The angle the Earth magnetic field mixed with the what? Horizontal. That is angle of this. So all the four are magnetic elements at a place. They are used to determine the position or the location of a body. Are you there? They are used to determine the position or location of a body. All of them call them magnetic elements. They are called magnetic elements. So when you have something like this, I have something like this as this is the horizontal plane. I have something like this as the Earth's magnetic field. Okay, so this is the angle, this angle theta, and this the magnetic field. The strength of this field is B. B represents magnetic field strength. So it's a vector quantity. So you can resolve it. You resolve it vertically, and also resolve it horizontally. When you resolve it vertically, it will be B sine theta, and when you resolve it horizontally, it will be B cos theta. Do you get that? So this is the vertical component. Are you there? And this is horizontal components. Okay. Provided the angle is here, it's with the horizontal. Are you there? Alright. So number 36. Which of the statements above are correct? 1 and 2 only. B 2 and 4 only. C 1, 3 and 4 only. D 2, 3 and 4 only. E 1, 2, 3, 4. So all of them are correct. So option E is the correct answer. So magnetic element are angle of declination, vertical component of the Earth magnetic field, the angle of dip, horizontal component of the Earth magnetic field. These are the four magnetic elements. So option E is the correct answer. Now for 36, option E is the correct answer. Now 37. For 37, you have to sketch. Give me a small sketch. 37, I'm having this 3-dimensional plane C. We're having this as B. We're having this as A. Which of the following statement is correct about it? Which of the following statement is correct about it? This diagram. If A is current, B and C are field and motion. Okay, they said the diagram below represents Fleming's left-hand rule. Fleming's left-hand rule. Fleming's left-hand rule. Is used to determine the force on the conductor carrying current. Fleming's left-hand rule is used to determine the force on a current carrying current. Are you there? The force on a conductor carrying current. This is Fleming's left-hand rule. It states that when the thumb, are you there? When the thumb and the first two fingers, I say when the thumb, are you there? When the thumb, the forefinger and the second finger, when the thumb, the forefinger and the second finger are stretched out. This is the thumb, the forefinger, the second finger, the thumb, the forefinger, the second finger. When these three fingers, the thumb, the forefinger and the second finger, when they are stretched out of the left hand, when they are stretched out in such a way that they are perpendicular to each other, when they are stretched out perpendicularly, are you there, in such a way that the second finger points in direction of current, in such a way that the second finger points in direction of current, are you there, and the forefinger point in the direction of the field, which is the magnetic field now. Then that's conclusion. Then the thumb will point in direction of force or motion. So that's what they are testing us on. Okay, now said option A, which of the following statement is correct about it? If option A, if A, that's the letter A here now, is current. If A is current, let me put I here, represent current. B and C are field and motion. B is field. Let me use capital B to represent field. Are you there? Then motion, and then C is motion. Let me use F to represent motion. Are you there? Which is force. Are you there? We normally have force, magnetic field, and current. Are you there? So let's now see. You have to position these your fingers in this order, and to confirm it, you have to position these your fingers in this order. Okay. The force is up, which is the thumb. Thumb is force. So take it up. You take this finger up, force. Then the magnetic field is here. Well, so this is our forefinger. Your forefinger must point in the field direction, in B direction, while your thumb will point upward. You position your hand like that. So my thumb is pointing up. Which is the force. Okay. This is my forefinger now, which is the field, is pointing in B. Yes. And field. While this one is pointing, this second finger is always the current. It's pointing in direction. So it's pointing down in this direction. Okay. That means that option A is correct. Which of the following statement is correct about it? Okay, let me. They now say They now said if A is current. So if A is current, let me put my fingers again. That if A is current, if this one is current, B is that B is field. Okay, and C, and then B is field. Okay. And C is motion. Let's position it again. This is motion. This thumb is motion. Put your thumb for that motion, for that force up. And you know that always our forefinger is our field. Our forefinger is our field. And always our second finger is current. So does it match? Oh, look at the finger. Okay, look at this, my thumb. My thumb is pointing in the direction of force, which is motion. This my forefinger is pointing in the direction of magnetic field, which is B. And this one is pointing. This is always our current. Second finger. Can is pointing in this direction, towards this direction. So, is it? So, and that's the correct option. Others will be wrong. If you follow the same method, others will be wrong. So, if you follow the same method, B, C, D, E will be wrong. Okay? So, in matter 7, option A is correct. So, if A is current, because when you put it this way, this one will still be your current. Okay, this one will be your current. I'll put it this way. To still be your current, because this one is always your current. Okay, and you can place your finger in that particular direction. It matches. Okay, it matches. Okay. Let's go to number. Okay, number 38. A transformer is used to operate Now it's calculation. A transformer is used to operate 12 volt 60 watt lamps. A transformer is used to operate 12 volt 60 watt lamps from a 240 volt AC source. Calculate the power loss if the efficiency is 80%. Calculate the power loss if the efficiency is 80%. A transformer is formula for efficiency for machine are there, whether transformer or the other mechanical machine. Efficiency equals to power output over power input. Power output over power input times what? 100. Okay, so a transformer is used to operate 12 volt 60 watt lamp. That 60 watt lamp is the output, is one that will light up. That 60 watt lamp is the output, is one that will light up. Now from a 240 volt AC, 240 volt AC, that is the input. Are you there? That's one that will supply the power. Okay, so and we know the power is what? IV. Are you there? Power is IV. So calculate the power loss if the efficiency is 80%. So I repeat the question again so I can get it. A transformer is used to operate 12 volt 60 watt lamp. That 60 watt lamp is the power output. Are you there? It's power output. From a 240 volt AC source, we are coming to 240 volt AC source later. Calculate the power loss if the efficiency is 80%. Efficiency is 80. Let's substitute. Efficiency is 80. Power output is 60 watt lamp. That lamp, the one that will light up, the rating of that lamp that will light up is the output. That's 60 watt is already in its SI unit. All over. We are looking for power input. We are not given. You must have one unknown that you look for times 100. So when you make power input the subject, power input and you call apply, you find you will get 60 times 100 all over what? 80. Okay, 60 times 100 all over 80. That is 60 times 100, okay, divided by 80. That's 75 watts. So the power input 75 watts. They put in 75 watts of power and it performs a work of 60 watts. So power is loss. Are you there? Power is loss. So always the input power must always be higher than the output power. The difference in the loss is the heat from the bulb. The bulb will be hot when it works for some time. So now the power loss will be the power input minus the power output. And the power input is 75 watts, power output is 60 watts. So when you subtract 60 from 70, you have 15 watts. That's the answer for that. So option A, 15 watts, option B, 20 watts, option C, 27 watts, option D, 38 watts, option E, 75 watts. You know we got 75, but that's not the final answer. Option A, 15 watts is the final answer, correct answer. Now let's go to 39. Let's go to 39 quickly. 39. So number 39, the root mean square of current in a circuit. The root mean square of current in a circuit is 12.0 ampere. Root mean square current, that is I RMS is 12.0 ampere or just 12 amperes. The root mean square of current in a circuit is this. Determine the instantaneous value of the current. Determine the instantaneous value of the current. We're looking for instantaneous value I equals to question mark of the current when the phase angle is 45 degrees. Phase angle phi is 45 degrees. That's symbol. So when the phase angle is 45 degrees. So tell me what formula are you going to use here? You know, we have different formulas under this particular topic, alternating current. We have different formulas. So we have I equals to I naught sine theta, sine phi. I equals to I naught sine phi. Are you there? When you look at this, I equals to I naught sine phi. We are looking for I, which is this. The phi is given at 45 degrees, which is the phase angle. Are you there? But I naught is not given. I naught is the peak current. The peak current or amplitude. The peak current amplitude. So we have to go and use another formula to get this I naught. Are you there? So let's go to high RMS. That's another formula. I RMS equals to I naught over root 2. So high RMS, root mean square, equals to I naught over root 2. So you use that formula first to get your I naught, then now come back to this. So I RMS is given as 12. We're looking for I naught over square root of 2. So that gives us cross multiply. So I naught becomes 12 root 2 amperes. So I naught is a peak current or amplitude or maximum current. Peak current, P-E-A-K. Peak current, you call it peak current, you call it amplitude, you call it maximum current. Are you there? But this is not the final answer. It's different from instantaneous current. Instantaneous current does not have any subscript, or you can put I. The RMS current is RMS. RMS is the subscript. The peak current is small zero as a subscript. That's the peak current. But the instantaneous current, you can put small letter I as instantaneous current, and you can spell it like that. So let's now go back to the formula and substitute. We're looking for I. Our I naught has been gotten as 12 root 2 sine phi. Phi is the phase angle, 45 degrees. So multiply everything together. So what are we going to get there? Sine 45 is 0.7072 sine 45. That is 0.7071. So 0 is 0.7071 multiplied by root 2, 1.4142, 1.4142, then multiplied by 12. That gives us 11.9. So let's use 11.9999. I equals to 11.99977 like this. So I is approximately 12 amperes. Approximately 12 amperes. I is approximately 12 amperes. So our option they said the root mean square of current in a circuit is 12 amperes. Determine the instantaneous value of the current when the phase angle is 45 degrees. It is just a coincidence that the IRMS and I are having the same answers. So just by coincidence, either it's just because this root 2, this 1 over root 2, sine 45 is same thing as cos 45. Sine 45 is 1 over root 2, cos 45 is 1 over root 2. Are you there? Which is 0.7071. Now it was just by coincidence. Okay. All right. They said number 40 now. Number 40. A capacitor. Let's go to number 40. Number 40. A capacitor is connected across a 120 volt RMS 50. A capacitor is connected across a 120 volt RMS, 50 hours AC source. If the capacitive reactance is 100 ohms, calculate its capacitance. Let's look at the parameters. A capacitor is connected across a 120 volt RMS. That is the voltage source, V sub S. Voltage source is 120 volts. Okay. Frequency 50 hertz AC source. Frequency F is 50 hertz. Okay. If the capacitive reactance is 100 ohm, that is cross X subscript small c, that's capacitive reactance is 100 ohms. Okay. Calculate its capacitance. Capacitance is capital letter C equals to question mark. So which formula is this? So the formula for capacitive reactance, X subscript C is equals to 1 over 2 pi FC. That is formula for capacitive reactance. So from here we just substitute and get our values. Okay. So what's our XC? Our XC is 100, capacitive reactance equals to 1 over, I will leave your answer in terms of pi. Then we take pi as 3.14. That's 2 times, what's our pi? 3.14 times, what's our frequency? 50. And what's our C? Capital C. Again for capital C. So when you cross multiply and make C the subject, you have C equals to 1 over 100 times 2 times 3.14 times 50. That will be your C. So that is 1 over 100 times 2 times 3.14 times 50. So when you multiply that, you have 100 times 2, 100 times 2 times 3.14 times 50. So that gives us C equals to 1 over 31400. 31400. So that means 1 divided by 31400. That gives us C, capacitance, equals to 3.18 times 10 raised to power minus 5. Are we there? Farads. Farad. You can convert it to microfarad. As a C equals to, let's convert it to microfarad. It's 31.8 times 10 raised to power minus 6 farad. Are you there? 3.18 and then minus 5 farad. I can take it like this as 31.8 times 10 minus 6 farad. So capital C equals to, because they are leaving the answers in farad. So this 10 to the power 6 is micro. That's 31.8 microfarad or mole. Micro. Okay. 31.8 microfarad. So our options is we have option A, 31400 microfarad. You know we got that. It's wrong. That's not the correct answer. That's not the end of the answer. Option B, 6445.8 microfarad. Wrong. Option C, 155.1 microfarad. Wrong. 106.3 microfarad. Option E, 31.8 microfarad. Option E is the correct answer for number 40. So thank you so much. I'm going to end it today. This is part 2. So please look at subscribe. Click on the subscribe button and the like button, and then you see the part 3 of it. Part 3 will continue from 41 to 60. Part 1 was 1 to 20. Part 2, 21 to 40. Then part 3 will be 41 to 60. So click on the subscribe button so you can able to see the videos I've uploaded, the solutions to others. Are you there? And in case, I always tell you, in case you need me as home lesson teacher for maths, physics, chemistry, foreign maths, technical drawing, I'm always there. So feel free to call me on WhatsApp. Your WhatsApp number is 090-745-26311. So that's WhatsApp number, and it's also the phone number that you can call. Are you there? This is Campus Academy, where we make everything easy and simple for you. Okay, so whether it be common entrance, WAEC, NECO, JAM, PSAT, checkpoints, coming for training, coming for lesson, coming for home lesson, and other things. Do you understand? So we are there. This is Campus Academy. Please don't forget to subscribe and click on the like button so that you can able to look at other videos in other subjects, chemistry, maths, further maths, physics, technical drawing and all that. Thank you so much. Bye for now.